Are there any questions on the take-home exam? Anybody has any questions? No? That's good. Okay, I'd like to continue to talk about quantum mechanics and crystalline structures. And then this is actually very important for quantum transport in nano-electronic devices. So this is very important for that. Then the reason is because you can divide electronic transport into 3 regimes. And then there's this microscopic transport. And then there's a mesoscopic transport. And then there's a microscopic transport. So in microscopic transport, we're talking about large devices. Large devices. This is, in the case of nano and micro devices, nano and micro devices. Okay, we have that kind of thing. And then, of course, in microscopic transport, you have atomic scale device, length scale, atomic length scale. So when the size of the structure is very small on the size of the atom, like what we've been talking about, crystalline structure, essentially we have many ions or atoms bound to the crystal structure, and then we are interested in wave propagation through this kind of structure. And then we are talking about length scale on the order of the atom size for atom separation. So this is definitely microscopic transport. And in this regime, wave physics is very important. The wave nature of the electron becomes very important. Okay. But then you go to the other extreme, which is macroscopic transport. And what happens there is that the crystalline structure is so large compared to the size or the wavelength of the object. Then what happens is that when you have a bulk material, bulk material is never a perfect crystal. It has imperfections, it has defects, it has impurities. Okay, these are not the ions, these are impurities. And it could be imperfection in the crystal. We see that if you have a perfect crystal, you can have a block wave. The block wave can move through the system without attenuation. That's what we found from this K omega diagram. We found solutions that might look something like this. So if you look at E, which is H bar omega, we have solutions where there's no imaginary part to the K, or is there an imaginary part to the frequency. So if you have a block wave, a block floquet mode that propagates through the crystal, you can propagate through the crystal without any attenuation. Okay, that is the characteristic of a block mode. It's like a waveguide mode. If you have a perfect waveguide, you can have waveguide mode that satisfies the guidance condition, and then the waveguide mode will just go through the waveguide without any attenuation. But the real world is not perfect. all the crystalline structures that we have impurities in them. So the electron wave will propagate for a while. Okay. You can think of this as a kind of electron wave moving through the medium under the effective mass approximation. We have derived the effective mass approximation, or the effective mass Schrodinger for this system. Schrodinger wave equation. So in that picture, we can think of this system being replaced by an electron with a different mass moving through this system with no attenuation. That is the effective mass approximation. So we can think in the macroscopic scale that we have such an electron moving through the bulk material under the effective mass approximation. But that electron, or electron wave function, is going to encounter imperfections in the crystal. And because of the imperfection, you cannot have a block mode. Those block waves will get scattered off this imperfection. And then you have to dope materials with impurities to make n-type materials, p-type materials. So the picture is that the electron will zigzag through the system, okay, due to scattering. And then there should be a concept of beam-free path. It's some kind of a path for which the electron can travel without experiencing a collision. Okay, electron will travel through the bulk material. This mean-free path actually can be on the order of nanometers to micrometers. Okay, for some materials, it could be on the order of micrometers. So we have this electron moving around. And in that case, it's better to think of the electron as a particle than a wave. And there is another requirement that you can think of an electron as a particle rather than a wave, that is the coherence length. So as an electron propagates, roughly it can be described by a wave function, okay? And then the wavelength, the de Broglie wavelength can be on the order of tens of nanometers, maybe 20, 30 nanometers. That is the de Broglie wavelength. Okay? But a lot of these box structures that we construct are many, many times larger than the wavelength. That's one thing. Another thing is that there will be phonon vibration or crystalline vibration. Okay, there will be phonon vibration and crystalline vibration, and that as the electron goes through this box material, it doesn't see a homogeneous background. It sees a background of ions or atoms that are vibrating. Okay, so this wave function is going to get perturbed as it propagates, not perfectly as a plane wave, but going to lose its phase shift, or there will be a phase drift. And after a while, as a wave propagates from here to here, it loses phase coherence with respect to the original point. Okay, so there's this coherence length concept, where if a wave propagates, if it's an ideal wave, it will be a perfect sinusoidal. Okay, then the phase at this point is locked to the phase at that point. But if there is randomness in the phase, then the phase might drift one way or another, and then finally, after a certain distance, the phase becomes random with respect to the beginning point. When the distance for which this wave loses its coherence, or become random with respect to the original point, we call this the coherence length. Okay, the coherence. So the phases of the waves are not coherent anymore. Okay, and this is important because if I have two wave functions, say e to the I k 1x plus e to the I k 2x. If I square them, if I find its magnitude square, for instance, I would have, if I call this psi 1 x and then psi 2 x, for instance. If I square them, I will have psi 1 squared plus psi 2 squared. And then there will be the cross term, psi 1, psi 2 conjugate. Or maybe 2 times the real part of psi 1, psi 2 conjugate, or something like this. If you square them, you get something like that. And this one is the interference term between the two waves. If the phase become random in this way, this average to 0. Okay? So if you have two wave functions, finding the energy is the same as finding the individual energy. So this becomes particle-like. A wave becomes particle-like when a wave loses its phase coherence. Instead of worrying about keeping track of the phase of the wave, you don't have to keep track of the phase of the wave because the phase becomes a random variable. Okay, the phase becomes a random variable, you just need to keep track of the energy of the wave. And keeping track of the energy of the wave is like counting the number of particles you have in a wave. So when a wave function loses its phase coherence, it becomes particle-like. So when two things are true, if the structure, if the length of the structure is much, much larger than the mean 3 part, and then this is also much, much larger than the coherence length, then you can actually think of the particles, electron, as particles rather than waves. Okay, then you talk about particle transport rather than wave transport. And then in that kind of regime, then you say that quantum mechanics is not that important, and then say if I have a electron drifting through the bulk material, I can think of it as being consisting of a drift term. Okay, this is minus the electric field. Okay, the electric field is going to cause the electron to drift due to the applied electric field. This is like a QE kind of effect. If you have an electric field, you have something, then you have this kind of effect. And then you have the diffusion term. Okay, so the transport of a particle through a bulk material can be described by what is known as the drift diffusion equation. And then what is important is that the first term is like Ohm's law kind of thing. Okay, this is electron density. N is electron density. Mu is like mobility of the electron. And so the first term is like the fact that it's like Ohm's law. We can actually figure out what the conductivity of this electron is by knowing the mobility. And the electron has been slowed down essentially by collision. In other words, the first part is essentially the particle density times the velocity due to drift times the Q, okay? And that the particle acquires only a finite velocity under the application of an electric field. That is Ohm's law. Ohm's law says that if you have an electric field applied in the bulk material, the electron is going to move with a certain velocity through this particle, okay? But then, if there's no collision, V is going to be a finite value. Okay, the electron, if you have an electron in the presence of an electric field, if you have an electron in the presence of an electric field, this electron is supposed to accelerate. Its velocity is going to get bigger and bigger if there's no collision. Okay, so the electron is going to have a velocity that goes up, but that is not going to happen. The electron is going to hit something, and then its momentum gets destroyed, and then it's going to move in another direction. So finally, the velocity is going to be finite. Okay, velocity is going to be finite, and the fact that we have finiteness of velocity due to an applied electric field is due to background collision. Okay, so the first term describes the kind of physics. The second term describes the fact that if the electron density is high, is going to give rise to equilibrium, and the electrons are going to push each other away. And this is the diffusion coefficient. So this second term is due to diffusion. When the electrons are next to each other, they don't like to be next to each other, they try to crowd each other out. And then you have a similar one for this when you replace n with p for holes. Okay, for holes. And this kind of transport is also called Boltzmann transport. Okay. This kind of transport is also called Boltzmann transport. So are there any questions regarding this kind of transport? Somebody asked me how to relate what we see here, what we're trying to do here in microscopic and mesoscopic transport to what we have learned in, say, ECE. Is it 340, right? You learned about Boltzmann transport and diffusion equation, the drift diffusion equation, and kind of thing. That kind of thing happens only at microscopic length scale. When the electron has a large distance to travel, it collides with the background crystal. Okay, then Ohm's law kicks in. But then in the microscopic and mesoscopic length scale, in nanoelectronic devices, we are making things on the order of maybe 22 nanometers now for transistors, and we're making a lot of very small devices. So mesoscopic transport and microscopic transport becomes increasingly important. And the electron can travel a long distance without collision or scattering. Okay, that's why we're studying quantum mechanics for nanoscopic transport. So are there any questions? Yes?
Can you give us some examples on what is mesoscopic transport and what is microscopic?
Microscopic transport, for instance, is the case of an electron moving around in an atom, electron moving in the crystalline lattice, okay, in the short length scale. You essentially have the soft Schrodinger equation, and those are the microscopic transport. Mesoscopic transport is when you make nanoelectronic devices like transistors on the order of 100 nanometers to tens of nanometers. Okay, so wave nature of the electron is still important. Scattering events are not dominant in that kind of transport. Okay, that we call mesoscopic transport. And what we learn in this chapter is very important for mesoscopic transport and microscopic transport.
So holistic transport should be...
Holistic transport refers to the case when an electron can travel a long distance without collision. Okay, so it should fall under this category. When you see that a block wave travels, it travels without loss. Okay, you can think of that as a holistic transport. But if you add imperfection in the crystal, you destroy block locate theorem. Block locate theorem doesn't hold true anymore. Then a block mode cannot exist. Okay. So we were up to the effective mass Schrodinger equation. We show that if you have an electron traveling in a crystalline lattice, you can come up with a Schrodinger equation with an effective mass that describes the propagation or the movement of the electron to that crystalline lattice. And somebody pointed out to me that I make a wrong statement about insulator, metal, and semiconductor. In the insulator case, the gap has to be large. If you have conduction band over here, and then you have valence band down here. This is an insulator, the gap is quite large. And then if you have a semiconductor conduction and then valence band, this is on the order of, I think, one EV or something like that. Okay, 1 EV. So it's quite small. And this is on the order of maybe 5 EV or something like that for insulators. Okay, you usually have a larger band gap between the conduction band and the valence band. And the larger this gap is, the harder it is for the electron to jump from here to there. Okay? Because you know that KBT is on the order of 25 milli electron volt at room temperature at 300 degrees Kelvin. So we have this Fermi Dirac distribution that describes E minus EC or E Fermi divided by KBT. So what causes this jump is the ratio between these two factors. If the energy is much higher than E Fermi, then the likelihood that there is a jump is not there. Okay, this is a Fermi Dirac distribution. It's controlled by KBT. Okay. So we derive the effective mass Schrodinger equation, and the equation that we derive looks something like this. And it's important for mesoscopic transport and microscopic transport. Okay, so essentially we have an equation that looks something like this. With an effective mass, Laplacian squared plus V psi of RT. You remember what V is in this effective mass Schrodinger equation? V is the, what was V that we used? Yeah, it's not that. We started out with potential that looks like that. Okay. And of course, in the real lattice, it might not look so nice. This might be the zero potential, and then in the real 3D lattice, it might look something like this. You will see a Coulomb potential instead. Okay, this is 3D. This is 1D. So we derived block-blockade theorem for 1D, and then after having derived block-blockade theorem, we say that the block wave has to be something of this form. It would be UK of R. This is a periodic function into the IK dot R kind of thing. We have a block-blockade wave that looks something like this. Okay? And then we say that when the wavelength is long, k tending to 0, uk of r is approximately equal to u0 of r. That is, you can replace this periodic wave function with its value for a DC value, a long wavelength limit. Okay, this could be a function of k. Okay. And then after having done that, we say that if you look at the band diagram, the band diagram always looks something like this. E versus K. And then we say that this is a parabola, so we can say that E as a function of K, or E sub K, can be written as minus h bar squared, K squared over 2m effective plus V. Okay, this can be written by this, approximated by this. So V is the bottom of the conduction band. If you have a valence band, V is the bottom of conduction band. Okay, we set that value to be V. And then when we plug this back in, we found that if you work on the left-hand side, you will find that the right-hand side becomes something like h squared, k squared over 2m plus bottom of the conduction band, this is ek. And then we replace that with minus h squared Laplacian square over 2m e plus v. Okay, V is the bottom of the conduction band, and then we get this effective mass Schrodinger equation. So this fact you have to remember. So we are deriving this based on the fact that the crystal is periodic and that is infinite in extent, but we can also apply this effective mass Schrodinger equation to a crystalline structure that varies slowly over space. Okay, so we can have cases assuming that on the length scale of the lattice spacing, those changes are small. For instance, we can assume that B is a function of R. Okay, which means that B might be changing as a function of R so slowly on the length scale of the crystal lattice spacing, the spacing might be very, very small. And over this length scale, you can still assume that the block theorems hold somewhat, and then you make the approximate argument that the effective mass Schrodinger still holds true there. Okay? And then you can also assume that the effective mass is a function of position as well, that it varies very slowly on the length scale of the lattice spacing. So we can apply that equation to cases where both the effective mass and the potential is a function of position. That we do all the time in the sense that if you have a p-n junction, for instance, and then if you look at the potential of the p-n junction is not a constant, if you plot it, it might look something like this. B, due to the formation of the depletion layer. Okay, so if we take the bottom of the conduction band to be RV, the bottom of the conduction band also can change over distance because there will be an electric field built up in the system. So the electric field might point in this direction, and there will be the difference in potential going from here to there. And in order to use the effective mass Schrodinger to model this system, you have to assume that B of x is a function of position. But if this B of x changes so slowly compared to the lattice spacing, then that's okay. Okay, that's okay to do that. And then in the case of effective mass, if these two are made of the same material, then it's fine. The effective mass doesn't change very much. You just dope them with impurities to get this kind of potential change. But if the two materials are different, then what we have is what is called a heterojunction. This kind of material, p-n junction, made out of silicon, for instance. This is called homojunction, where you have one type of material, but then if you have two types of materials, then you can form what is known as a heterojunction. In a heterojunction, then you might have effective mass that are different over these two regions, okay? But then, for the sake of simplicity, we're going to assume that these junctions are slowly varying. Effective mass changes gradually, which is of course not true. Maybe changes on the length scale that is rapid compared to our lab fabrication process. But then, on the length scale of the crystalline lattice, it's still slowly varying. So we would still use the effective mass approximation to approximate heterojunction devices, even though it's not strictly valid right at where the junction is. In that case, we just assume that over the length scale of the junction, there are many, many lattice spacings around. Okay. So examples of heterojunctions are if you make aluminum gallium arsenide devices of 3,5 compounds, and for instance, one very common semiconductor compound, I think Subhan Lin and a lot of you know a lot about this because they're from the micro lab. aluminum gallium arsenide. So you change the component of X to change the behavior, essentially the EK diagram of this thing. By changing the amount of thing, you can change the band gap and the kind of thing. By adding in sufficient amount of aluminum, by doping the thing, you can change the band gap, and then you can also change the effective mass. But they have to do this for lattice matching. You find that with certain compound, you can make it a compound and get the lattice spacing matcher, so you can make heterojunctions without lattice mismatch. Okay, when you can make heterojunctions without lattice mismatch, then the device can be made more easily. Otherwise, the thing will start to break up at the lattice junction. Okay. So, how do you approximate a rough Venn diagram in this kind of devices? Then? There's something called the Anderson's rule, okay, which is not absolutely correct, but it's approximately correct. Okay. So if we have this Anderson's rule, we assume that if we have a bulk material, okay, you might have a conduction band over here. And then it will have a valence band. Over here. And you can control the band gap of this material by using your compound semiconductor growth technique. Okay. But then there's this work function called the electron affinity function. This is vacuum level. So the chi is the amount of energy needed to take an electron from the bottom of the conduction band to vacuum to make it a free electron. Okay, you can do photoelectric experiment and try to bombard this thing and figure out how much energy it takes to take this electron from the bottom of the conduction band to make it into a free electron. So if you have the next material over here, you might have a band gap like this. But then its value has to, its vacuum level has to line up. So this might be chi 1, this must be chi 2. That's Anderson's rule. Okay, so if you line up these two materials, you will have the junction approximately. Of course, this junction you cannot make it to be abrupt. You should think of it as a gradual junction so that you can still apply your effective mass Schrodinger. Okay, a lot of the things that we have about block theorem doesn't go through anymore. But then you can make devices like this, and then you can add another one. So if you can put three of them together, you put the vacuum level, all the vacuum level lines up, then you can have the conduction band that looks like this. And then the valence band might look something like this. So an effective mass electron will travel over here, and it will get trapped over there by this kind of heterojunction. Okay, this is chi 3, chi 2, chi 1. And this is conduction band. Valence band. And this is how quantum wall is made, for instance. You can make quantum wall by making this kind of devices, and then you can engineer quantum wall. Okay. But let's talk a little bit about this effective mass Schrodinger when the effective mass is not a constant anymore. How should we rewrite this effective mass Schrodinger equation when the effective mass is not a constant? should be write it like this. It turns out that we shouldn't write it like this. ME is a function of R. We have to rewrite the Schrodinger equation in such a manner that we actually have to sandwich the effective mass, which is a function of position, in between the gradient operators in this manner. This is very important because of how we define particle current. If you write it in the other way, particle current is not conserved. But if you write it in this manner, then you can show that particle current is conserved. Okay? So if you have such a kind of Schrodinger equation, if I write it in 1D, then it becomes quite obvious. If I write this equation in one dimension, I have, say, partial x, 1 over MEX, partial x, psi E of x t plus V of x, psi E of x t. Okay, this is just writing the effective mass Schrodinger in one dimension. And by just staring at this equation, you know what the boundary condition should be. If I have an interface here, I have